Hello.
Hello, good morning. You're the host. So I have a repair to make on one of the links.
Okay. If you hadn't said that, I was going to let you know it's pretty much the same thing.
I went over in class briefly how to fix it directly in the URL, but I'll go ahead and get it fixed while you do the thing.
Yeah, that's generally what I do, and it almost always works.
And in terms of the lecture material, I didn't get to the latter part, so you may need to dwell a little bit on the different tests that we're demonstrating in the lab.
Okay. I guess there's a waiting room, so I'll hit the admit button.
Oh, I didn't. Yeah, you're the boss now. You don't have to do admit. You can always go to participants and bring up the participant panel. And down at the bottom, there is
I see it now.
option to disable the waiting room, and then it just automatically lets people in.
Good.
And the recorder is running. I'm going to go ahead and fix those links. If wait till a few more people show up, and then you can get started. And I should have the links fixed by then.
I think we're at the age or drawing close where people won't know what Men in Black is.
Well, they'll make another installment of it. They're going to have to get someone other than Tommy Lee Jones. He's getting kind of long in the tooth. Will Smith is no spring chicken anymore either. I guess you're right. Okay, fix the links.
What a great movie.
Oh, and the Lab22 notebook will have to be manually downloaded because I don't have an internal link for it.
Right. I went here and saved. So I did.
Okay, so it's in the Blackboard. Don't break now. Okay. Laboratory, go to lab. Oh, it's not even there. Okay, that's the broken link. It's in there. Right there, fix that. Clean. Rebuild everything.
Let's see. It is 9:06, but we only have 15 people. Oh, well, it's being recorded, so let's go ahead and start. So let's see. On Monday, I mentioned the term of hypothesis testing. Now we're really going to dig into what that means. If we think back to the last lab, make sure everything works again. There. Let me think. Think back to the last lab. We had 2 sets of data, and we did a bunch of stuff and decided that the normal distribution data model gave us a good fit for both of them. We did this based on just visual assessment, and we didn't actually do anything to verify that. And now we're going to change that. So let me think. Where got to get the data. No, not that one. Let's see. Is the CSV in the lesson webpage?
It's in, I'll go ahead and I'll send you the link. It's still not correctly updating the links. It's very annoying.
Yeah.
Okay, I did
Such
that.
is life. Okay. So while I actually get the data to, oops, don't want to do that. Undo. I think I can undo. There it is. Can't download lab using that link. Well, that's the one that worked for me. I see. I'll see if I can get that. Okay. I have that now. Yes, that's a good point. The data is on the server website, so that will be the that's where I'm going to get it right now. All right. Let me just.
Oh, my bad. I ran the wrong script. Duh, no wonder it didn't work.
Okay. All right. With that fixed, if you run into an issue getting the file once Dr. Cleveland actually gets the link working for everybody, let me know and we'll take a look at it. But we're not going to wait around because I won't have time to get through what we need to. So what are we doing? Well, we're doing the normal making a data frame out of a CSV thing that we've done a couple times. We've got a first set, second set, and here we're going to make some variables for our mean and standard deviation, unlike what we did last time, and it's just helpful. And then if you remember, we went and took those, the mean and the standard deviation, locked them in place, and then recreated the data randomly. So we had our first set of data, and it's got stuff in it. Number. This is this first set one. Well, this has a mean and it has a standard deviation. So I'm going to use those to create a new set of data, same length, except they're going to be random. But I'm going to make sure that no matter what this random collection of numbers is, that it will have the same standard deviation and have the same mean. Now, how do we do that? Well, with the magic of using NumPy. We're going to randomly sample from a normal distribution using U1, which is the symbol for generally used for the mean, and the standard deviation. We want 100 elements in each one. So we have set 1, set 2, and then set 1, random sample, and set 2, random sample. Now we'll write it in. Now we plot them. And as you can see, they are pretty good about overlapping. Now I can generate them again. And just like before, they're slightly different. The green and the red will not change because those are the actual data, but the orange and the blue will change slightly every time I run this because they're being randomized. Here's the box plot showing again the 5 points of data. We've got the range, the mean, the quartiles, all that fun stuff. But this is just a recap of what we were doing before. But now we're actually going to get into something better than looking at this visually and saying, yep, it's a normal distribution, or no, it's not. Let's see. One second, I might be able to share a link, copy link. Try that, and if that doesn't work, I can put the file in directly. Okay. So we're going to use a normality test, and it's called the Shapiro-Wilk test. It's just the people who came up with it. And what it's going to do is say, look at set one. I want to be able to say with a 95% confidence that this is either a Gaussian or not Gaussian distribution. What's Gaussian? It's normal. So the name, so Gauss is a mathematician, one who discovered the normal distribution, so it's named after Gauss. But the normal distribution is the name because it's so darn normal. So I've already ran this before, but since we've randomized our data, we'll run it again to see, is set one normal or not? All right, let's check. Well, obviously I didn't change set one. We're not randomizing set one, we're randomizing set 1s. So set one and set two are probably Gaussian with a confidence of 99% here and 98% here. Not super important that you understand the specifics of what a confidence is. We'll get to that in a bit, but suffice to say, the intuitive understanding of 99% confident is good enough. Okay, so we're, let's see, blah, 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 blah. Okay. All right, so Dr. Cleveland points out something worth talking about. In the instructor notes for the lesson, we have some explanations on what this kind of means. So if you are confused and want to look at a different time, you can come look here. I get rid of that. So there's the normal distribution. Yep. Okay. All right. And so we have the two sets of data that we went out and actually collected. We say those are probably Gaussian. Let's check the randomized one. So I'm going to take set one and set 1s, and we're going to use another test. And what we're going to do is say, I want to be able to, here, I'll make this a little more visual so it's easier to visualize. Duh. All right, we got our first one. This is the data we went out and collected. We'll say this is set one. Now, if you remember, set one on the big graph was really small, but if we were to zoom in to only look at it, it would look something like this. So we went out and we have set one, we plotted it, and we've determined with sufficient confidence that this is a normal distribution. Okay, that's nice. What about the one we randomized? So what we want to do is take the randomized one and see, are these two from the same distribution, and what's the likelihood that they are? Because again, when you're in any kind of statistics, which, let's face it, if you're in data science, you're going to be doing a bunch of it. The good thing is you're just going to be using a lot of statistics tools. You're not going to have to really understand the derivations and stuff like that. But you want to be able to say how confident you are that two things are from the same distribution, or how confident you are that it's normal, because you very rarely get to say that, yes, 100% this is or isn't something. In fact, let's just, yeah, that's suffice. That's good enough. You really get to do it. So we want to say how confident are we that these are from the same distribution? And so set 1s has been randomized again. So we'll run this again. And we're going to use this test to see if they're probably from the same distribution. Let's check. Okay. So we printed that they are probably from the same distribution, which means that we have at least a 95% belief in that. Let's do the same thing with set 2 and set 2s. Okay. We believe they are probably from the same distribution. Now, this should come as no surprise, because our eyes aren't lying to us when we look here. Both visually, set 1 and set 1s, they overlap a lot. So much so that if you were in the business, so gun to your head, set 1, the blue and the green, are they related in some way? Are they completely unrelated? I would say no. I would say there's, because no matter how many times I randomize, they're always overlapping a lot. So it'd be a losing bet to say that set 1 and set 1s, blue and green, are completely independent. They don't have anything to do with each other. It would be visually, it would be unwise to say. And also, I know that they have something to get in common. I know for a fact they have the same mean and the same standard deviation, because I made them that way. So it should come as no surprise that our test here says they probably come from the same distribution. Now, I've randomized them again, so this will be running the test, and it'll probably say the same thing because of what I just explained, but the numbers will be different. So again, no matter how many, well, that's not true. You could randomize set 1s and set 2s forever and ever, and maybe sometime in the next 10,000 years, you might get this to say they're probably not from the same distribution. Okay. So rather than just blitzing through everything, let me pause there, because I have gone through quite a bit. Does anybody have any questions or are a little confused about any part about what I've just been talking about? We had a recap, a test to see if we think that the first set of data is normal, and then a test to see if the generated data is from the same distribution as what we collected. Now would be the time. Let's see. Okay, well, haven't received anything. So either everyone's taking a nap, which naps are nice, or everything's at least mostly clear. So let's move right along. So let's say that we're confident that set 1s and set 1 are probably from the same distribution. Same thing with set 2. Now, if we think back to, you know what I'm going to do? I'm going to clear all the outputs because there we go. The last lab, we left off basically asking the question, green and red, do we think they are from the same, do we think that they are different enough? Do we think they're different? That was the question. But well, now we actually have a way to ask that. So we're going to use the same test because we're doing the same thing. We're asking, do we think that these things are from the same distribution? So let's check it out. Do I think set 1 and set 2 are from the same distribution? Well, they are probably different. That is what we've been told. Quite confident too. Let's check the same thing for the randomly generated ones. Probably different. Now we can state at a 95% confidence level that set 1 and set 2 are different. Now, what the heck does that mean? Well, this is saying I'm 95% confident. Okay. Well, it took me a long time to actually truly understand what this means. And I don't think that in one lecture I could get it across. But we do have something that we can do that can kind of show how this works. So let's go back to let's go here. Set 1 and set 1s. That's the ones we're comparing, right? What I'm saying here is run my test. And if you are with at least 95% certainty, sure that they're the same from the same distribution, okay, that's good enough. Well, let's change that. Let's say 50-50. If you're at least 50% sure, say that they're from the same distribution. Okay. Well, look at that. They appear to be different now. What about that? Oh, they're different. Still different. Well, what if I make this 25% rather than 50%, rather than 50-50? Okay, we think they're from the same one. All right, that's good. Let's keep going. The same one. How many times would it take? Probably too many to get it to have different outputs. What if I did this? So this is saying I want you to be 99.9999% sure that they're from the same distribution. Well, that works too. But if I were to go the other way, let's see, 0.99, we'll get the exact opposite. That we're basically saying be 99% confident that this is the case. So the p-value is just, I think it's explained here, that, oh, here it is. It's the probability of the collected data given that the null hypothesis was true. Okay, so rather than me just saying what the null hypothesis is, let me ask you guys, what's the null hypothesis? Assumes the statement to be true. The default assumption. Yeah, okay. That's that. I can dig that. So the null hypothesis only makes sense if we have something that we can test to be either true or false. Is something true or is something false? This only ever works on things you can test that way. Can it be true? Can it be false? The null hypothesis is saying we're going to assume that it's true. So before we even do any kind of test at all, we assume that it's true. And then what we are then saying with all these nice numbers, 95, 99, blah, 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 what we're doing is we have our distribution of stuff. And we've assumed that our claim is true. And what I'm saying with a 95% confidence is that I'm going to draw an interval here. That's 95% of everything that occurs. I'm saying that what we're going to find falls in this boundary. Now this is the standard, 95%. But why is that? Well, it's 2 standard deviations away from the mean. That's why. I believe you can go 3 to get to 99. That's usually not used. 95 is the standard. So we have these, oops, I think I drew it out too far. We have these very unlikely observations, which you can consider them like, you've heard the term random noise. When you go out and collect data, there are going to be outliers. When you go out and measure, or you poll people to get their height, there are going to be people who are 4'5" and 8'9". They're just exceedingly rare. This goes again to why this is called the normal distribution. When you go out in nature and collect data, and usually in the physical world, you're almost always going to have it this way. Okay, so that's what the null hypothesis is. It's the assumption that whatever we're testing is true. So what are we saying here? Well, let me change this back. I'm saying I have a 95% confidence that set1 and set1s are from the same distribution. So I could replace this with fail to reject the null hypothesis. And I could replace this with reject the null hypothesis. So I fail to reject the hypothesis that set1 and set1s are from the same distribution. Okay, so hopefully that does something and doesn't confuse everybody. Let's look at another example. I'm going to need that one too. No big deal. I'll just download it. Okay. All right. So here we have some data. Hooray. It kind of looks like this. We have scored or recorded the data of a whole bunch of students. Got the gender, race, ethnicity, the level of education of their parents, some lunch data, and the interest. Well, the real thing we were wanting to look at is the scores they get on a test for math, reading, and writing. All right. So I was going to ask, how can we figure out some nice descriptive statistics about like how many people were tested and all kinds of stuff, but it's right here. The describe method is very nice. Anytime you make a data frame, I would recommend you at least run the describe. Okay, so what do we got? We got 1,000. The mean on the math score is 66. 1 second. So we went over this in the lab in which we first looked at the describe method. Only the math score, reading score, and writing score show up here. Now, why is that? Why doesn't it show the lunch and blah, 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 blah? It's because the describe method is working on numbers and everything else. What's the average of, what's the arithmetic mean of the test preparation? Is it completed in a half? It's not a number. We can't take the mean of it. So we have the mean, standard deviation, and all the other nice stuff of the scores. So let's save those. Okay. And let's visualize things. Oops. Oh, gives us a nice segue into when you see a giant red box, usually that means something's wrong. See how it says warning and it did what I wanted anyway? You can ignore this. This is a warning that I won't even explain what it means. Just don't worry about it. Okay. So we have the, let's see. Set 1, which is the math score, is in the dark blue. We have a histogram overlaid with the line. So you can see the dark blue is for math, the orange is for reading, and the green is for writing. Now, visually, I could make a couple, see if I could lay out some patterns, but visually only gets you so far. And again, can you send the link? Oh, I can try. All right, see if that works. Again, somebody went out in the real world and collected some data. And what do we see? Well, it may be skewed a little bit to the right, but this is another normal distribution. At least, in fact, I don't know that because I haven't actually ran the test. But it sure looks normal to me. And if we were betting if it's normal or not, I'm going to place my money on normal. Okay. So we have 3 samples and the same population. Seems there's no significant difference between all of them. Let's set the null and alternative hypothesis to as follows. The null hypothesis is that there is no difference in performance of students between math, reading, and writing. Now, I have done this lab before, and I ran it earlier, so I already know what's going to happen, but I'm going to pretend I don't. I would say there's no difference between reading and writing. I'm not as confident saying that there's no difference between math and the other two. So let's see what happens. Well, I guess before I actually do it, and it's on the screen, you could figure it out yourself, but can someone explain to me why I can't just test them all at once? Why can't I just do this all in one big go? And I don't mean run them all at once. I mean, I can't do one test on all three tests, all 3 math, reading, and writing to test if they're different or not. Yeah, that is it's more specific than I was expecting. The answer was that the Mann-Whitney test only compares 2 to each other. Yeah, that's it. Because we're asking the question, the test we have answers the question of, give me 2 things, I'll tell you if they're different. And we can't hand it 3 things because I don't know how to answer what do you mean by different or not. Difference is a if we consider different to be a function, it returns true or false. It takes 2 arguments, x and y, the things to compare. If I were to be comparing 3 things, in order to do that, I needed to compare them 2 at a time. So I'm going to compare math and reading. I'm going to compare math and writing. I'm going to compare reading and writing. So kind of like I just guessed, and it's not a hard guess because you can see how close the green and orange are, and that the blue one, while you still think it's like no surprise, this is from the same people. I would I would be confident to say that these students are not as good at math as they are at the other two. And sure enough, the test indicates that they're not. They're from different ones. Now, I would be curious, to what level do I need to change the p-value? So to make it not be different. 95%, which is this, is 2 standard deviations. I don't remember exactly what 1 standard deviation is. I think it's like 60 something percent. I think it's 68. So what's the backwards of that? It'd be what, 32? Let's try 1 standard deviation. Still thinks they're different. But yeah, visually lining up with what we're actually testing. Now look at this. We have a test that's comparing all 3. Look at that. That's fancy. Probably different distributions is what it tells us. Now, what I could do, set 1's the math set. What I could do is be a little sneaky here, just to make sure my test is actually working and it's not just spitting out different every time. Why does increasing the p-value make it more likely for the be seen as the same? It depends on what you mean by increasing the p-value. When I quote unquote crank up the p-value, what I'm actually doing is lowering it. So if I wanted to increase the p-value, I need to decrease this number. So this is saying be 99% confident. This is saying be 99.9% confident, so on and so forth. Maybe if I crank this up to 11, yeah. This is a level of precision. I'm not even going to count the zeros. This is a level of precision that is absurd in statistics. It's simply, I'm not a statistician, but I would say trying to calculate something to that level of precision just doesn't happen. Now, what you could do, if you want, is you could find the amount of zeros to where if you run it like half the time, it'll be the same, half the time it won't be. The way to interpret this is a little tricky because the data is not changing. And it does not make it more likely that one is the same as the other. What it is doing is changing how specific the test is. So if I say I have a test, you don't know how it works. All it does is it takes 3 things. It takes a thing to compare, another thing to compare, and then a level of precision. I could just be flipping a coin back here, 50-50, who knows? That's what this value is for. It tells me how specific to be. And the 95% is just the standard. Hopefully that is useful. Okay, so as I was saying, I actually ran into this yesterday in my office hours. So I'll ask you guys, what is so if I have my data, let's say set 1, what is the correlation coefficient? So some value between -1 and 1. What's the correlation coefficient of set 1 and set 1? So to be more general, I'm asking, yes, that's correct. What is the correlation coefficient of a set of data in itself? It's 1. It is perfectly correlated. And as far as I know, that's the only time that happens. The only time something is perfectly correlated is if they're the same. Don't quote me on that. It's just what I think, what I remember. So if I want to make this test tell me if it's actually doing something, I'm going to say, all right, instead of comparing set 1 with set 2 and set 3, just use set 2 twice. And there we go. They're probably from the same distribution because I know set 2 and set 3 are probably from the same, according to this. So yeah, I know that the Kruskal test isn't just flipping a coin. So it's saying 95% of the data being, the question is, is this, can this be interpreted as saying that 95% of the data being compared is similar? Again, I'm not a statistician, but I would say no. Here is my interpretation of it. I've got the data. I don't chunk up this data at all. It cannot be divided. What this is saying is I'm looking at my data. Well, actually I have two of them, right? I have two chunks of data, and I'm not saying 95% of this one's similar to 95% of this one. Yes, it's that I am 95% sure that these two are close. They're similar. Another way to interpret that is if I ran this test 100 times, are they similar? That I would get at least 95. Yes, they're similar. And that's not saying that I'll get 5. No, they're not. I'm saying I will get at least 95. And we saw what that is like when I started changing this. So I'm saying I'm going to get at least 95. Now I'm saying I'm going to get at least 99. Okay. Now I'm saying I'm going to get at least 999 out of 1,000. So somewhere between 900 and 999 times out of 1,000, it's going to say that they're different. So somewhere between 0.01 and 0.001, you can find it if you want. If you can get this to be exactly 50-50, then you found the point to where the precision kind of breaks down. Okay, let's look at another example. Let's imagine we're in charge of a website and we want to be able to track some sales. We want to change the design of our add to cart button because maybe it'll increase our sales. So what we do now is I go to a group of people. And what I'm going to say to them is, all right, look at our buttons. Half the people are going to go to the old one, and half the people are going to go to the new one. And I want to know, does the change I made increase the sales? So this is what's called an A/B test, also called with the term split testing. And what it does is it tests small changes. And this is usually what you want to do when you want to decide if you want to actually do something or not, like changing the button. Why not test 3 options at once? Why not try the regular one, the green one, and then maybe a blue one? Well, they're both green, but you get the point. You can have as many changes as you like. But the more perturbations you try, the smaller of samples you'll have for each case, and the harder it'll be to actually get good data. So as I've said, like when we were doing the linear fit kind of thing, when you have like B0, B1, and B2, it is generally a good idea when you're limited on resources, at least, and your brain power is a resource, to try to only work on one, as the fewest number of things you can. Okay, so let's assume we have 1,000 users. We sent 550 to site A and 450 to site B. In site A, 48 made a purchase, and site B, 56 made a purchase. Is this a statistically significant result? That's the question. All right. So the rate, sorry, why weren't exactly half sent to one site and half sent to the other? You can send as many to one direction as you like. Don't know. We can change this, and I will in a minute, but you don't have to do half and half. Now, sending 5 to one and 995 to the other would be silly, but for some reason or another, 550 went here and 450 went here. All right, so what we have, the rate of people on the rate of purchases of people sent to the old button is about 8%, 9%. The rate of purchases of people sent to the new button is 12%. So, hey, we want to change the button, right? Well, I don't know. Let's actually do a test here. Now, this will be the first time we run into something that's not the normal distribution. What we have here is a binomial distribution. If two options are available, I got door A or door B, and we have people who are going to choose door A or door B, we don't actually have the normal distribution now. So we're going to be using this one. All right. So look at that. Here we can see that the group B has an edge because we want the number of cells to be positive. We want more cells than not. But it's certainly possible if we took two random points that A might actually be higher. How do we know that? Well, remember that this distribution for B isn't saying that if I randomly get something, it's going to be the average. It's saying that it's going to be in here somewhere, and I can say 95% of it's in this interval. But it is possible that I get a 40% on B and a 60% on A. It's possible. But I could tell you that the mean for A is less than the mean for B. So since we're actually interested in the average number of cells, let's approximate this with a normal distribution. So let's reformulate here. All right. So we've changed from the number of actual sales to the purchase rate for group A and group B, which is kind of what I was talking about here. The purchase rate for group B averages out, what we saw here. And the purchase rate for group B, A, averages out here. So we've removed the effect. Oh, I guess it is time. All right. Well, I don't want to blitz through everything and just confuse everybody. So we will take a look at what needs to be done in the homework. I noticed like everybody, we went from like 20 people to like 3. So let's change gears. All right. Just like we had last time, we have boxes from Walmart and Amazon. And what we are wanting to do is rather than do all the, you're going to be doing a lot of the same thing. I think, in fact, these 3 are the same. But in addition to doing the visual plotting and all that fun stuff, we actually want to run the test. Now notice we have an alpha of 0.1. Okay, so we know which distribution this belongs to. We know which test to use, and there's examples of actually calling the functions all through the lab. So sorry I couldn't get through everything, but we had some link difficulties, and it's not worth it to rush through stats because then you just get lost. So before I close, does anybody have any questions, comments, or concerns? The last part in the lab. This one? Interesting. Questions: how can we find the sets that are different? Use that one here, right? Oh, well, here, I'll give you a hint. Well, I guess I don't have to give you a hint because this is the actual lab. Here's how we would do it. Remember how I made everything? I made set 1 into set 2. Well, I know if I run this, it is guaranteed that they're going to be the same. Guaranteed. Why? Because set 2 is the same thing as set 2 is the same thing as set 2. Okay, well, let's change one of these to set 3. This will be the same if set 2 and set 3 are the same. It will be different if set 2 and set 3 are the same. Okay, so I know set 2 and set 3 are the same. All right, let's check set 1 and set 2. Okay, these are different. Let's check set 1 and set 3. These are different. So I now know that set 1 is different from both set 3 and set 2. And I only use the Kruskal test. I didn't have to use the Mann-Whitney. So there you go. Bonus answer, I guess, for everybody who stayed or watched the recording. Yep, it's a puzzle box, but instead of two, you're trying to ask it a question about two things, but you have 3 entries. Well, just make 2 of them the same thing. Okie doke. It'll be good enough, and I'll see you all on Friday.